Hey, and welcome back to another crafting a crawler. We are back looking at map generation algorithms again. We've been getting some really good results out of this. Some of these are, quite frankly, some of them are less functional as a map, but more abstract work of art. So yeah, I've done some work on this last night in that I wasn't overly happy with how we were rendering out the maps. So I did a bit of work to get these rendering a little bit nicer. So kind of like this, they all look a bit like old school Polaroids now. But let me see if I can... get a bit more space on the screen. Yeah, so we've got this sort of more Polaroid thing. We've got a natural frame around everything. So I think these are looking a little bit better. We have yeah, so like something like this. I'm not 100% sure this would ever be a good map, but I mean, there's a lot of, although there is a lot of stuff in the way there, this could make quite a good little map for some sort of range combat. Running around here with a bow, there's lots of things to hide behind, so it could be useful. And the symmetrical ones look really fancy, but not 100% sure if the diffusion limited aggregation that we implemented last week would be that useful there, but yeah, this is quite nice. But what we did find is it works really well with this cellular automata. So we get quite a nice looking large cavernous area here. So I think this is probably going to be our go-to for cave boss battle arenas for sure. Though the Drunkard's Walk does give us a nice style. But yeah, we have today though. I want to look more at one other thing that I worked on. I set this up as well, which is using the same techniques we used at the end of the last video to create this style. The binary space partitioning to get the rooms, then the Drunkard's Walk for the room, carving out the rooms, then the DLA to sort of fluff out the edges a bit more, and cellular automata to smooth everything out, and that gave us a really nice sort of look. So I tried it again with more rooms, and we got quite an interesting sort of result out of that. It's more windy sort of cavern, a bit more room-like, I guess, but yeah. But today, one thing I want to look at is, so we've been connecting our rooms together, and we've been using some very simple stuff to connect them, mostly look at the order in which they were generated and connecting each room to the previous. But we get some sort of weird generation at times with that, like overlapping connections where something's sort of coming in here and going all the way down. And then something over here is like connecting all the way up here. So we get like double corridors next to each other and things like that. So I want to try and look at a way to fix that. And one of the ways to fix that is going to be to make sure that every room basically connects to its neighbors rather than other rooms quite a distance away. So I hope that will give us some better results. And to do that, I'm going to generate the edges so that we can connect every room to every neighbor. And then I'm going to add some stuff to prune off some of the connections. So we get basically just one flow around. We don't get many loops and stuff. So to do that, we are going to look at something called Delaney triangulation, which has been on our to-do list for a while, and that's the given a bunch of points, we basically find a pattern where we can connect all of them in in a way that where the paths don't the connections between them don't overlap. Thankfully, Wikipedia has an algorithm document for this. Well, sorry, has some various algorithms documented for this. One of them is the Boyer-Watson algorithm. So that has some pseudocode in here, and we're going to try and implement this today in our generation algorithms. So one of the benefits of moving our image generation as well is that I should hopefully be able to get more visualization of what we're doing out of the code. So as we're adding it, we'll sort of try and visualize how things are working. So what we are going to do a Boyer-Watson no, these are the wrong way around. I should be able to. Cannot track these. There we go. Yep. So we're going to look at the Boyer-Watson algorithm. What have we called these? Yes, this is a Boyer-Watson edge generator. Using the Boyer-Watson algorithm to generate non-overlapping edges. Between the rooms. So, first up, we're going to need some points. We're going to want this to copy the same signature as our other. Spent too much time on Windows and forgot my hotkeys already. We're going to want to generate some edges. Return an empty string for now. So, and then probably want to generate get a bunch of rooms. We do have a simple room generator. That does take the context. We could do. Let's do something a little bit hacky for now. we go global rooms, and we go underscore rooms equals result. And then when we run this, we should now have a underscore rooms set. Cool. So we're going to want to visualize what we're doing. So we'll create an image. Let's go for an RGB image, and we'll set the background to white. There we go. Display image. We get an empty image. Cool. So what I think I want to try and do with this is we want a drawing context. Yeah, so the first thing we want to do is take our rooms, and we want to get points from them. So points is equal to center for room for room in rooms, and that'll give us some rooms. And then with this we can go for X and Y in points, draw a circle on the coordinate of that to be X and Y. Radius is equal to 1, and fill okay, so we've got an image here. We'll go for 2. Yeah, that's a bit more visible. So we've got an image here, and this is our points drawn on it. Let's actually increase that times 3. Okay, so we've got our points and they're scattered around in here. So what we want to do is basically create the triangles that fit between each of these in a way that they don't sort of overlap. So we wouldn't join this point to this point, because then we wouldn't be able to join the additional ones. So to do that, we need to start with a big triangle around the whole thing, and then we're going to divide that triangle up into smaller and smaller pieces. So to get that, first we need to get the bounding box of the entire set of points. Let's update our imports for a sec. We're going to import math. The lack of an S there is constant. Constant nails on blackboard moment for me, but we'll try it to get on with it. So yeah, okay. So we're going to create a box. Actually, we could do this the inefficient way. Yeah, because, well, we're not going to have too many points, I don't think. We are looping over x and y every time there, though. Yeah, I think for the amount of points we're going to have, it's not going to be too important. Okay. So given that, we should now be able to draw a rectangle. xy equals got a width and a height, and then I think if we consult the docs for this, we're using the pillow library, and on the image we have, we want the draw. And we call the rectangle method. Rectangle, 2 points defining the bounding box. Okay, cool. So we want that. Oh, we did have a little bug there. We'll fix that. All right. Then here we want a width plus the bounds 2. So bounds 1 will be the top, the left. Sorry, bounds 0 will be the left, 1 will be the top, 2 will be the right, and then we'll to add the. And our final one will be the bottom. So we pass these in, and we should be able to visualize where our bounding box is now. Let's put that in, like so, and then we probably just want to have a light color on this. Let's go for that going to be legible? Just about, but not quite, maybe not quite enough. Here, yeah. So now we can see we've got the bounding box for the entire, all of the points. I think what we want to do is then we'll minus, we'll expand it by a little bit, just give us some leeway. Because we want to make sure that all of the points are within the square, not on the edge of it. So yeah, so now we need a triangle that will fit that around that box. Okay, so then so triangle is equal to 3 points. And to get the triangle that fits into our bounding box, we want to go grab the width and the height. Okay, so triangle is 3 points. So we want the first one will be bound 0, so our left coordinate minus width divided by 2. And then the top, our second coordinate will be bound 2 plus half the width, and then the top again. And then we want bounds 0 plus half the width, and then we want to add the height again. So when we do that now, we should have a triangle that encloses that. That encloses the entirety of our points. So we'll try that. Draw a polygon, and this will set to the triangle. We'll outline this in we're going to outline this in red. So now when we're running it, what do we want? We want to offset this the same as all of the others that we've done. 4x, y in triangle. So there we go, yeah. So now we get a triangle that fits around our bounding box. The next step is to find if we take the pseudocode for our algorithm, sorry, I noticed I've had that up on the other, had that up visible to me, but I haven't been showing it to you guys. Yeah. So we paste this in and comment it. Okay, so we've got our points list. That is what we want to coordinate. We want a triangulation, which is going to be a list of triangles. Sorry. And then we want to add the super triangle to the triangulation. And this must be, as I said earlier, this must be large enough completely contain all the points in our point list. So that is what we've done here. We found the bounding box. We found the bounding box and we found a triangle big enough so to fit all of the points in our point list. So we're going to append that triangle. So then we want to look at each point. So for x, y in points. Okay. So for each point, we want to find the bad triangles. So bad triangles is an empty list. Then we want to loop over each triangle, and if the point is inside the circumcircle of the triangle, then we want to add the triangle to the bad triangles list. Okay, so we're going to need another helper for this. So a circumcircle is a circle that entirely encloses the polygon, or well, the triangle in our case. So all of the points of the triangle will be on the circle, and then we want to find a circle that hits all of those points. So there is some maths to calculate this. Yeah, so we want to find the central location. Sorry, I've lost that. Circumcenter coordinates. Okay. So yeah, so if we take this mass, we can find the center point, and if we can find the center point, then we can look at any of our other points to find the distance to it, and that will give us the distance between our. That'll give us the distance between our. That'll give us the radius as well. And if we have the center and we have the center point and we have the radius, we have a circle. So we're going to want a new helper now. Def circumcircle of the triangle. Yeah, we'll have a point, and we'll go with an integer distance for the radius. So we're going to want to cache the values from our triangle. So we want AX and AB, and then we want to go D is equal to 2 times A AX times BY minus CY plus BX CY minus AY plus CX AY minus BY. Hey. Copilot gets a cookie, as it actually got that right. This is where the things, these AI large language models are actually useful. And every now and then they can just spell out exactly what we were planning to write. It saves us some time. Okay, so next up we have 1 over d. So yeah, if we look at that, so what we've basically done is translated this mathematical equation here into code, and that becomes our D assignment here. So now we're going to look at the other two. So these are effectively 1 over d times x squared plus, ax squared plus ay squared times by minus cy. We do the same for b with cy minus ay. We do the same for c with ay minus by. So it looks like we're going round in a circle around the points. Subtracting the next one from the following one, from the one after that, as we times it by the sum of the square of both coordinates values. So with that in mind, we then get here x equals 1 over d times ax, times ax to the power of 2 plus ay to the power of 2 times by minus cy, and then we add to that the same for b and the same for c. And then we do the same for the y coordinate with the x coordinates instead of the y coordinates. This is basically the same as dividing, so we can add the divided by d at the end here instead. Take it out at the beginning. Let's try and break this up a little bit, make it a bit more readable. This is actually remarkably similar to my day job at the moment, so I'm always tempted to claim that I'm a Greek translator. As a skill, in that most of the mathematical notation uses Greek characters, so and I spend most of my life converting that into plain English for programming. Yeah, okay, so then the radius is going to be the distance between this point and another point, and the way that we get that is we take the square root of x squared I think it's x squared minus y minus y squared plus, sorry, no, yeah, the square of the two x's and the square of the two y's. I think that's correct. Hang on. Let's go Google Pythagoras theorem. No, sorry, no, I did get this the wrong way around. So it's, sorry, it's AX, yeah. Sorry, it's the square root of a to the power of 2 plus b to the power of 2. More sensible notation, so that it translates here to, yes, yeah, so the size of our thing is going to be x minus ax raised to the power of 2 plus y minus ay raised to the power of 2. That is distance. We might actually extract that as a function. A and B. Yeah, that is the same as what we had. So that becomes the distance of xy and triangle A. Sorry, the first point of the triangle, and we can return xy and the radius. Now if we take that, I think when we append our triangles, we're going to need these quite often, so we'll go triangle and circumcircle of the triangle, and add both of those to our list. I think in this we will then draw a circle as well, and that will be we'll draw the circle in blue or green. Sorry, green even. Okay, so now we've got a circle that encompasses our triangle. So then if we come back to our algorithm, so what we want to do is for each triangle in the triangulation, if the point is inside the circle for the triangle, we add the triangle to bad triangles. So for each in the triangulation, we want to go through these with the indexes. I think we will go if the distance between our point. Sorry, let's use the point rather than splitting it into x, y, because that's what we actually need to pass around at the moment. So if the point and the circle is less than the radius, then we're going to append the index to our bad triangles list. So that's given us now, so we've done that, and we've done this piece, so we can take that out. And then I guess we want to go if the polygon and this is going to be a set of edges, which I think will be a tuple of point to point. So for each triangle in our triangle, we then want to go for we want to get the edges for the triangle. So that'll be the connections between them, and we want to check that against, so for each edge in the triangle, the edge is not shared with any other triangle in bad triangles, add the edge to the polygon. So we'll go for should have been I here actually. Yeah, for I in that, then we want to add the index, and then for each index, I'm going to grab the triangle, and then for J, J and edge, no, sorry, J, in the triangulation, if I is equal to J, then we continue, and then for the edge in edges, and see, and this is why we don't trust the AI as 100%, and why you should never let an AI do the coding for you, because it's completely wrong here. What we want to do is actually if edge is in okay, we want to create the okay, we got the other edges. Okay, for edge in edges, for other edge in other edges, then we want to so we want to check if the edge is equal to the other edge, or if the inverse is equal. Actually, we can make that a set instead. Then we're going to for each if edge in other edges or the reversed version is in other edges, then continue, else we want to add the edge. So how are we doing so far? So for each of the bad triangles, if the edge doesn't match any other triangles, for each edge in the triangle, if the edge is not shared by another triangle, we add it to the polygon. Then we want to remove the bad triangles. So for I in, we want to sort the bad triangles. So we want the biggest number first, and then we'll just take them out the triangulation. And for the edge in the polygon, for each edge in the polygon, we want to calculate a new triangle that meets that point. So we're going to go, triangle is the point and the two edges, and then we're going to append that into our list of triangles. Okay, so now we've got this whole bit done. If we have a look at what we've got now. Interesting. So we don't have any triangles now. Means we have a bug. So for each point in the triangle, we find the bad triangles. Okay, and then for each of the bad triangles, we find the edges. Okay, sorry. This bit here is not quite indented enough. So yeah, so for each edge, we have a look. Yeah, we loop over the other triangles. We skip the current one. We look at the other edge. We grab the other edges. We doing that more than once. I think edges for triangle. Yeah, this will make things a little bit more easy to read. So edges for our triangle there. And then we want to look at other here. Let's have a look at what values we're getting. Okay, here is the problem, because we only have one triangle. When we loop over the others, we are not adding in the values, so what we need to do instead of this, we go edges dot remove the edge, and then after the loop we go does that work? We'll have to loop over and copy of the edges, so otherwise we're modifying it as we're looping it and it gets upset. Okay. I mean, there's definitely something happening there. It's still not quite correct though. Okay, something is not entirely correct here. So let's visualize what's happening as we go. So I'm going to take an image and we are going to set that down, and then for each of our bad triangles we are going to draw onto that image. What did we do before? Here we go. We want the draw context. For our image, so we've got a new image, we're going to draw the polygon and then we're going to display it straight after. And then that creates a, then we should get a polygon. So we will then add a second image here where we draw each of the polygon lines. Oh, where's our code? Okay, so definitely split it up right there, but then it's losing. It's then losing something. Okay. Yeah, so we've got then got the sides of what we carved out here. Why is that not drawing? With that one, I think we'll also try and draw the so we can get the So I'm going to draw the point, point onto here. Yeah, so we've got the point there is in the triangle. We get the sides, but when we try and draw these, they're not drawing. Create a new image. The edges are definitely 2 points. So why are these not rendering out? I mean, we can see, kind of see that this is split in this one, but then when we draw it again, suddenly we're losing all of our values. So something is actually going very wrong. So what we want is so we have our bad triangle. Okay, so we loop over each and we add the bad triangles to the list. Draw those and those are fine. We then get the edges. For each of the bad triangles. And we loop over all of the other triangles. And we compare the edges, and if the edge is in any of the other triangles, then we remove it. And then we add those edges to the polygon. We remove the bad triangles. Then we create a bunch of new triangles. Then when we try and render out edges, they don't show up on the screen. Yes, this is hang on. Okay, is this because we have decimals mixed in? I think when we create our circles, yes, so these are actually returning the wrong type. Maybe start with rounded x and y, and then we round the radius. Still getting weird points though. We want to make sure we're working with integers here. So we're losing triangles as we go, which is not what we want. Okay, let's so we know this bit works correctly. It's here that it's starting to go slightly square. We could just draw the new triangles. Okay, so yeah, something very weird is happening. Okay, so we remove the triangle, those triangles, and then we have our edges there. We know they're there. Create the triangles. Okay, hang on. Let's look. There's 4. So for each triangle, if it's in the triangle, let's just do the first loop through this. So we have our first one. Here is our big triangle with the dot, our point, and then apparently the added, and then we've added the triangles here. So it has added them. For some reason when we try and draw them out, it's like, hang on. Oh, this is so stupid. I am apparently an idiot. This is why none of it has worked. So we want to draw the edge. So we want to draw a line of for the value in edge. Yeah. So our line, that should be fill. Okay, yes, so we've carved out that polygon, and then we fill it in. So next, this one, it finds all of these circles in the circumcenter. And then we still lose things. Oh. This was not particularly clever. Yeah, so this is flipped. Yes, that should be. So we were removing everything that was present in another circle triangle rather than the ones we wanted. So there, so it carves that out. Still missing. So it's getting a bit closer, but it's still missing some stuff. Okay, we're getting closer. We're getting closer. Oh, welcoming crumbs. As naked and afraid. Series starting again. Oh, good luck. good luck. You'll probably need it on that server. So let's have another look at this. So we have found the offending triangles that are in the way of us creating our new point. Don't expect to win or make it to the end. Well, I guess you definitely need the good luck then. We then remove all of the bad triangles. We then render that out. Sorry, yeah. And then we try and add our edges back. So this is where we're going slightly square. So let's have a look at that. Let's look at our edges before and our edges after. So first up, all the edges survive. Oh, no. Yeah, okay. I think I see what's going on here. Sorry, we are we're only meant to be checking the other bad triangles. So if other is now equal to the other triangle, you don't actually need the triangle there. So the circle there. So let's give this another look, and we get that. So we're getting closer. So this is finding these triangles, and this one's finding these ones, but then it's losing this edge here. When we recreate it. Though it does seem to be constructing it correctly. I still think we're losing some of the edges though. Oh, hang on, wait, this is why it's getting confusing. We're drawing regardless of whether or not we're removing or not. Okay, so now if we step through the algorithm, we have our big triangle, we choose a point, and we find the offending triangles, and we carve out, remove them, take the polygon that's there, we drawing the new triangles. Then we do the same again. So okay, so we've got these two are problematic. So we get this shape instead. We carve that up into triangles. Yeah, and then our next point, we get more. We take the shape and we carve it down more. And as we get to the end, we end up with a spread of things that do not overlap. Everything here is connected without lines intersecting, other than the points themselves. So we can take out all this rendering. No, that was not. So let's take that out. Take that out. Yeah. Okay. So the next step is then to remove. To map this back into meaningful edges. So we want to go for yeah, then we want to remove any triangles that do not match our images. So we want 4 iron range of the last element. No. Yeah, 4 I in range of triangulations to -1, and we want to go -1 step. And the stop is the yeah, the stop is exclusive. So we'll go over each of our triangles, and then in reverse order, and we'll go if we'll go triangle is equal to triangulation I 0. We'll take the triangle and we'll go any we'll go if triangle 0 or triangle 1 not in points, or triangle 2 not in points, then we'll remove that triangle from the set. Now when we run, yeah, we started. So sorry, we messed this up. So we want to go from last element, which means we need the length -1. And now our set of triangles doesn't escape the bounding box anymore. Which means we now have this part. We could probably actually just look at width and height. Don't need all of the extra space anymore. Yeah, take the triangle out. So yeah, now we have a, here we go. So now we have all of our points and we have the connections between them. So if we then use this on our random one, we're not returning the results though. So with that, we want to go for result. Result is equal to an empty list, and then otherwise we want a lookup table for our points. So we will go point I for, yeah. So now we'll be able to look up the indexes, which means when we iterate over here, we'll be able to do the lookup for triangle 0 to triangle 1, and that needs to be a tuple. We have 1 to 2 and 2 back to 0. And then we can return our result. Here we get all the mapping rooms. So now we get something that connects all rooms to all rooms, which is not particularly that useful, but it's a good start, because now that we have a set of connections, we can then prune that, start pruning that set of connections. So yeah, so these will all connect to the neighboring, to their neighboring rooms. So this one is connecting to here and here, and this one is connecting here, here, and here, I think. Yeah, so we get a nice split. But what we want now is to start looking at some maze algorithms. So let's take that out for now. We'll save values in memory for now. Okay, so let's let's start with our maze generators. So first up, mark down. So we've now got all of the rooms connected. Now we want to prune the connections. Hey there, Splash, welcome in. We now want to prune those connections down and get just the ones that are important to us. So there is just the ones, we want to basically have a tree that doesn't, where things are, each room's sort of connected once. So if we have a look back at our documentation, we have, for that there is an algorithm called Prim's algorithm. This will be probably the first one we'll look at. And what we do is we connect it, we then sort of take the connections and we prune them down so that we've just got a sensible sort of set of connections. And each thing is sort of connected in once to, and like we get some dead ends and stuff, but we don't really get loads of loops. So with that in mind, we'll go for Prim's algorithm. Where's this? This is, I've got them the wrong way around again. Okay, so Prim's algorithm take a edge generator. And I think we'll default this to the Boyer-Watson for now. So yeah, so these also will be edge generators, but there'll be a special case that wrap another edge generator. This is not what we're after. Yeah, so, and they will adapt the generator that we have. So if we look at the pseudocode for Prim's algorithm, this needs to stop. Alright, so every time, so we need to record the cost of each item in the graph. So we're going to store that and the edges that they connect for each item, what the edge it connects to is. And we do that by setting the cost to infinite for every item, and then we set a sentinel flag for value for each edge. So we'll probably use none. Then initialize an empty forest F and set Q of the vertices that have not been included in F. Initially all vertices. Okay, so we have an empty list set and a set of everything, and then we, until we have run out of stuff, we find and remove a value from our set with the minimum possible cost. We add that to the forest, and we loop over the connecting values for that. And then we set the costs and the edge values, and then we set every value in our forest. We return the edges. Okay, so we're going to want the costs for each connection. Wait, this is not. Okay. Let's have a think how we translate this into our Python code. Okay, so I think we're going to want to start out the same as before, and we're going to turn these, we're going to want points rather than so we're going to want points rather than the rooms. We're also going to want to get the edges from our actual generator. So we had each of these is now going to have a weight. Oh, sorry. Yeah, sorry. So yeah, we're going to want to get the points, same as we used in our last function, and then we're going to want to go get the actual edges, which will be coming back from our internal function, and then we want to go that the weights, we want to record some weights for each of our functions. So as we'll need this to calculate the cost. So we also probably want the length. So we want to get the, no, go for length, it lines up a bit nicer. There we go. So okay, so we've got our weights, and then for each of the edges, yeah, we want to assign the distance between the 2 points as the weights. Yeah, this here is going to be, so that gives a lookup table for our weight. And then what do we have? So we need costs, which is going to be after infinite for every item. Then we have edge, which is a list of integer or integer or none, and we're going to set that all to that. And then we have the forest, which is a set. We pick a random item to start with. Yeah, so we're not random, and then we set the cost of that to 0. Then yeah, and then we want to process every item in the set. We want to loop over and process every room after this. And then if we have a look back at our room, so we want to find the. So we don't really need the F and Q sets as these are defined, because Q is basically just F and Q. Well, one is derived from the other, and the full list. And because our rooms are numbered 0 through to n, we kind of know what the full set is. So with that and F, we should be able to. So we want to loop over. Oh, sorry. We're going to touch each item once, but we want to find the item has the minimum VAT cost. So to do that, we start with that, the highest possible cost we can have. We then do for I in range length if the cost of I is less than or equal to min cost, and I is not in forest, then we want to do min cost is equal to cost I, and v is equal to I. So yeah, because this uses v for our current item. Okay. So now we know what our item is. Then we want to forest.add v, so that is now in our forest and we won't process it again. And for what was it using? It was okay. So now we want to loop over and find w. So for every W, if W is not in the forest, and the weight is smaller than the cost of W, then we want to set the cost of W and set the edge. Okay, so yeah, sometimes these things are not the most well described. I do wish I could just go through the whole of Wikipedia and add sort of yeah. I feel like I'd really like to just go through the whole of Wikipedia, go through every single maths article and every single program article, and just put a very basic Python script or something for that expresses exactly what is happening. Like in code, because often the code is much simpler than to understand than often the code is much simpler to understand than the explanations or the random Greek bloody maths notation. But I've noticed in the past, if anyone tries to do anything like that on say Wikipedia, then everyone gets upset, because if you touch the math stuff and you put code on it, then they get upset because it's not in math notation anymore, and that upsets all the mathematicians. And if you do it on any of the other pages, then everyone gets upset because, oh, you did it in this language, why didn't you do it in insert random other language? It's like, no, it's just, it's like we just need to pick a nice, easy to understand language and just rewrite everything in code on there so that people can actually wrap their head around what they're meant to do. But what I think it was saying is that, okay, so we want to go for each W in the range. Okay, so for every value of W, if the weight of V and W is not 0, and because that would mean that there isn't a connection there, as our connections are the distances, and W not in forest, and cost W is greater than the weights of that, then we set those two values. Yeah. I think that's correct. I think this is what it was saying. Okay. So now trying to figure out what the hell. So now we've figured out what the pseudocode meant. Let's try and figure out what the hell it does. Okay, so we have our forest. So we go over each, and we have this edge. This is a lookup table for the we're missing one crucial piece at the end, which is return. When we return it, we want v and edge. V and edge v for v in for v in forest if edge v is not none. Okay, yeah. So for everything in the forest, for every value in the forest, we want to return that and the edge we associated it with here for as long as there is a value for it. So let's try it and swap that into some of our generation stuff now. So if we put that in here, we get nothing. Okay. So something went wrong here. Let's see if we can figure out what. Let's try drawing it. So let's go. Image is equal to pure image dot new. We're going to go for a black and white image, width and height, and we'll make it black. So for each edge, for each of the edges that we got from our original generator, we're going to draw we're going to draw a line. Points A and points B. We're going to fill that at 128. Let's go for half the value. And then for each value in the forest, we're going to go point for V and the point for tree if it is none, then we continue. Okay. So actually we got some stuff earlier, so we should be able to go. So we might, can we do that? Okay. So we do get some rooms out of this. I added this image in and then forgot to actually draw it. So So let's see what else we have. This. Wait. Oops. That is so that should be outside of the loop. So we do have a solution here, but it's not. Oh, sorry. And this we want it to be 2 for 5. Yeah. So now. No, this is still 64. Here we go. So now we can see this is our original everything connected, and then we've got this connection here. Okay, so that's actually working correctly. So then if we run here, here we go. So yeah, so this is now connecting. Actually, I might leave these in. These are kind of cool. So we can see the original layout, and then we can see how we stitched it together. So yeah, so we get a nicer layout now because everything's connected to a neighbor. We're getting fewer overlaps on the random. And then if we look at our BSP one, if we run this one, yeah, we can see the layout here and how that translates into our actual map. And the same here. Okay, so, yeah. Okay, we still probably need to do a little bit around the connections. I think we maybe need a tunnel boring algorithm that minimizes the number of pixels used. Or added, or maybe we go direct. And we possibly need to find a way where we get a good sort of dish or style connection. That will give us better borders here. So it's still not, we still haven't achieved perfection, but we're getting closer, I think. And yeah, these are laying out much nicer, more nicely now. We still get a few oddities, so this one's connected here. It would have been possibly nicer if it had gone that way. So we might need to do something around overlapping of the to make the room selection, the route selection favor routes that don't overlap, but this is looking better. I think. Yeah, this one's a bit weird as well because it's gone down here and yeah, if it gone this way it would have been. Okay, so I think that, yeah, I think the tunnel generation could be a little bit better, but all in all, I think this is definitely improving the way in which we are generating things. Let's try. Let's try it out in some of our more complex examples. Okay, yeah, so that's, I think that's I think it's working a bit better. Actually, yeah, I think. Yeah, I think there was a lot more connections accidental connections before. So I think now it's the roots are spreading out a bit nicer. Ooh, okay. Oh, that is a nice layout, that one. Okay, so I think this is good. So I think we've got now a smarter interconnection. So what we've got here, what this here is referred to as a minimal spanning tree. Basically, we're using a maze algorithm to, or graph algorithm. We're using some graph theory and to figure that out using Prim's algorithm. But what we also have is, well, given the name, no surprise, is a maze. So we do have we have Delaney triangulation now, and we have a minimum spanning tree. So that's two more things off our to-do list. And then we want to look at mazes. So now that we have a maze algorithm, all we really need is rooms and edges to satisfy that. That's up. So if we come back to our room placement stuff, we've got the BSP. So I think we will add code mark down above that. I think we're going to add a grid room generator. So if we have a grid room generator, we should then be able to go where is our simple one? Here it is. This is the simplest. So we'll take that as a basis. And then we want grid. And we're going to want X, Y, and spacing. So we have the context. The context has the width and height on it. So we're going to want to go context. So we're going to calculate the size of each room. Okay, so we're going to want to go the context.width minus the spacing divided by the number of items. And the same for the height. So we want to go minus the spacing. If either of those are less than 0, then we're going to return nothing. Else we will, for actually, I think I'll set this to the max of. Yeah, well, I think we'll say a room has to be least 5. No. So yeah, a room has to be at least 1 in size. Yeah, so we're going to say our width and height have to be at least 1 for each room. And then we'll go ix equals 0 and y equals 0. Well, iy is less than y, yx is less than x. Result is equal to a empty list. So we're going to loop over and we're going to append a new item. We're going to plus the spacing. We're going to append a rectangle, and then we're going to add the spacing. No, sorry, yeah, well, ix is less than context.width minus the width minus spacing times 2. Yeah, and this one's going to be the same with height. Then we're going to add there, and we're going to go reset ix there and increment iy. And by the end of this, we should have a set of rooms. So we say x is equal to 5. Okay. We get a simple maze. But then if we increase this, we should get a slightly more complicated maze. To 40 by 40. Okay, no, okay, now the complexity is getting a bit. Okay, that didn't actually render properly. It's actually working on the lower levels. Okay, so we have a maze here. Not a particularly good maze, but it's still a maze. But I think the connections are a bit weird here. So we probably want to make sure it's only connected to the ones above and below. So we probably need a new edge generator. Def edge grid. This needs to return an edge generator. Okay, so we want to connect it to its cardinal neighbors. So if I is greater than 0, then okay, let's go IX and IY. Oh no, consistency will make sure we're still going across X first. So then, all right. So if IX is greater than 0, then we want to append IY times X plus IX, IY times then IY times X plus IX minus 1. Okay. And we want to do the same with IY. So we want to take 1 away from IY here. So that should give us the 2 neighbors. And then we want to make sure that X is less than, IX is less than X minus 1. And if that's the case, we want to add 1, and for this one we want to check less than Y minus 1. And then we want to add 1 there. This should give us a grid. Where all of everything's connected to its cardinal neighbors. Oh, we're missing some. Oh, and then we need to return the generator from here. Okay, so it's not the best maze generator out there, but we do have a series of interconnected rooms. We just need to now try and find the optimal slicing. Oh, that's gone a bit. 20, things get weird at 20. So it looks like 19 is about as high as this will get. We can probably tweak this a bit later to get a better size out of it. But yeah, okay. So we've got, yeah, it's, as I said, it's not the best, and it seems to favor randomly going up in. Yeah, I kind of see a bias in the algorithm here. So you can sort of see the start point is there. Let's have a look at some other. Well, actually, I think I will call it here for today. This is, as I said, this is not maybe not the best. Maybe not the best maze algorithm. Prims, although. Although it does, yeah, I think we probably need to adjust the. Yeah, I think, I think what the problem is that each of the distances between these is the same, so it's basically picking the first one each time, which is giving it a very uniform layout to it. Whereas if we take the values here, I think what we need next is, so we get the minimum cost, then we go for if options is an empty list, and then for that, if the let's take this out for a sec. Yeah, so we go like that. So then we go for, we look at everything. If the cost is equal to if the minimum cost is not infinity, then we're going to loop over and we're going to find everything that matches. And we're going to store those in a list. I'm going to keep attaching those, and then we're going to go v is equal to one of the values from options. So now we're randomizing the value we choose. So if there are two equal cost routes, we will pick one at random. So these still seem to be working. Then we'll come to this more. Here we go. Yeah, this is a lot more maze-like. So it was a case of, it was because all the weights were, the distances between all the rooms were the same, and we were weighting based on that. We were losing, slightly losing it with our connections. So everything, it was always returning the same direction. Because all of them were the same. So by adding our change, what we've done is we've picked a random route value of all of the directions that had the same cost, the same distance. So every link that was the same distance is now put into a pool, and we pick one at random. Can we get something a bit? There's still something that's bugging me here. What I really want is to get a little tiny sort of old school maze. So tunnel simple. Okay. What if we increase the size of the tunnel brush? That was too many. Aha, okay. So we've got 9 by 9 squares. I wonder why it won't go smaller than that if I increase the value though. That's something to figure out another day, I think, but this is... Okay, so yes, this is a lot more maze-like, I think. as we run things, we get this would be an absolute horrible level to traverse, right? Okay, so yeah, it's like spawning into this and then having to navigate around. It will be in the sameness. It's like, I mean, thankfully, one of the side effects of Prim's algorithm is that it's kind of biased and will bias towards a lot of short dead ends. So like a lot of our dead ends are quite short, but I wonder what the largest distance is. That's another tool we're going to have to add to our collection to find the optimal sort of entrance and exit positions on our map. But yeah, this is starting to look far more maze-like now. So I'm going to call that successful, and I need to figure out what idiot mistake I made here that is blocking us from having smaller rooms. But once I figure that out, I'll probably do that off camera. We'll be able to get even more detailed mazes as the room size gets smaller. But yeah, I think that's a good start on our maze. On our mazes, so the grid, yeah, we've got our algorithms to carve these out, and it's kind of interesting. It's adding to our toolbox the same as everything else, right? So in this case, we're using exactly the same algorithm to get this maze, as we are to get sort of this room connection or this room connection, and it's like everything else in our thing. We're basically building a little toolbox of things to layer on, to put together to give us our final generation. I think when it comes to using something like this in the game, just looking at this gives me anxiety as a player, right? Like having to traverse all of this is going to be a horrible level, but we could maybe mix one or two in, right? We could have like one maze, or we could use this to generate a separate thing. We could maybe have a labyrinth entrance as a POI in the dungeon, and then as you enter that, you sort of get transported to a map that's been generated with the dungeon, with the labyrinth, with a maze algorithm, and then sort of traversing around that, trying to find something. Put some Minotaur enemies in here. Make it optional. It could work. I would be interesting to see, though, as we play with the maze generators and get better result looking mazes, how that will translate back to these generators. So as we improve our actual maze generator and we get a better looking sort of grid based maze, how would that map back to our non-grid based setup? And we could get some really interesting results emerge from there. But yeah, I think it's getting it's getting close to dinner time here, so I am going to call the stream, and then I can go and investigate putting some food in my belly. But I think we've definitely made some progress. So I don't think I want to remove. If we look back up at our to-do list, we've got a lot closer. I don't think I want to remove maze generation just yet, as there's some other algorithms we should probably look at. If we can get a nice looking maze, that would be great. Voronoi cells are actually kind of related to the Delaney triangulation, so we might actually be able to get that knocked out in the near future. But we're getting closer to having completed like the tunnel carving part. The biome mapping is going to be a more interesting one. So at the moment we're generating a map of air or walls. So something like this is either we've got walls and we've got air. The biome mapping will be where we start to mix in, okay, this is like swamp versus grassland versus desert style stuff, and we give some variety into the map. So yeah, I think next stream we'll probably continue looking at maze algorithms. I'm going to go read everything I can in the meantime on those. And if you want to see where we land with that, then give the video a thumbs up. Smash the subscribe button and hit the notification bell, and I will hopefully see you in the next one. Bye.